Please join me in welcoming to the Distinctive Voices podium, Dr. Marcia Rieke.
All right, good evening, everybody. Boy, it's nice to see so many people in person after, I don't know how long I've given only Zoom talks, and it's the last part of the joy of JWST is that we're getting to make talks in person and see smiles on faces and so on. So back in 1998, I responded to a call from NASA headquarters for scientists to say they would like to participate in planning for the James Webb Space Telescope, although at that time it was called the Next Generation Space Telescope, NGST. And then there's a long story about how the name got changed, which I won't go into right now. But so I've been working on this project since 1998. And the proposal for NIRCam itself, the camera whose development I led the team and organized the science team and so on, the proposal was written mostly in 2001 and it had to be submitted in March of 2002. And then we got selected to actually be the team. I got the phone call in June of 2002. So I think that means if I count up, there are a number of you folks here who weren't born yet. So this has been a project long in the making, but I think it's proving to be, I hope everyone agrees, worth it. So what is on the screen right now is one of the first, what we call early release observations. It's a target in the southern sky called part of the Carina Nebula. Carina is the name of the constellation this happens to be in. And this is a region that's forming new stars. And the part that looks like blue sky is actually an area where some newly formed stars have blown out all the leftover material from which the stars were forming. And the bottom part that looks more brown colored is actually where the new stars are forming out of a collection of gas and dust. Now, one thing I want to emphasize about the colors in this picture, as I'll explain in a couple minutes, the Webb Telescope works in the infrared. Your eye can't detect any of the light that went into creating this picture. It's all infrared beyond what your eye can see. So the way the picture was made was by taking pictures through different, what we can call them filters. If you've ever played around with black and white photography, you can have pictures through a piece of red glass or green glass or whatever, and we have the infrared equivalent. And a very good crew at Space Telescope Science Institute figured out ways to assign colors that your eye can recognize to different ones of these infrared wavelengths to make what we would call a false color image. And the colors are chosen to kind of highlight interesting things in the picture and help you visualize what's going on. So that's a little bit of the story behind this picture. A funny little anecdote about this picture is that my husband, who also works on the Webb project, found on the internet a place that was selling Webb regalia, souvenirs, whatever you want to call it, like my earrings here. He found bedroom slippers with this picture printed on the slippers. I think I know what I might get at Christmas, but we'll see. Okay, so this little collection of pictures shows the launch. The mission was launched from French Guiana, which sounds a little bit strange. Why not from Cape Canaveral? Well, this project involves not just NASA, but also the European Space Agency and the Canadian Space Agency. And the big contribution of the Europeans was the rocket ship itself. And so we got launched on an Ariane 5 rocket made by a French company, and they launched from French Guiana. And it was actually kind of interesting to think about the fact that this French rocket was actually, for this class of being able to lift as heavy a weight as Webb, was the most reliable rocket. But even then, I have to say, Christmas morning, it was a little bit nerve-wracking till it went off, because a rocket is just a controlled explosion. So if you lose control, we won't even think about it. So Webb got launched, and then in the lower left part of the pictures here, and I'll show you some more about why it had to be folded up, but the telescope and its sun shield would not fit in the nose cone unless they were folded up. And so the first thing we did on orbit was to unfold, get everything into position, and then there was quite a while of getting everything aligned. And there were a number of people who were skeptics that this unfolding, which is very complicated, that it would actually work, and it worked perfectly. And I think part of the reason it worked perfectly was because we had practiced and practiced and rehearsed, and we knew we had to get it right, because this telescope is now 1 million miles away from Earth, too far to send any astronaut to go service it. It's 4 times further away from us than the moon, so that puts a little perspective on it. And in fact, the orbit is kind of shown schematically here. And the telescope this is not really to scale. So here's the sun, and maybe I'll point with this one because that one's getting faint. So here's the sun, here's the Earth with the moon, and then out here is where Webb is, at a place called the second Lagrange point. And that's a special point from the perspective of gravity. And the virtue that it has is that the relative orientation of the Earth and Webb stay the same as they all go around the sun. So that makes it easier to send commands, get the data back down, and so on. And another good thing about being here is that this sun shield here not only blocks the sun, but also anything that light or heat that might come off the Earth or the moon. So it's a very good place to put this kind of a telescope. Now, let's see, this was October 2018. We had a meeting here down in Manhattan Beach at the Northrop Grumman facility, and the telescope was in a clean room there, and it was mostly but not completely deployed, and that's as close as I ever got to the telescope. And I was wearing the same outfit here. So I don't wear my clothes out too fast. And this character is my husband, who is the lead U.S. scientist for the mid-infrared instrument. So our family has connections to 2 of 4 instruments. So at least I got to see it pretty close. Okay, now why would we build a telescope like this that cost $10 billion and took over 20 years to build? I mean, that's a pretty astounding project to sign up to be part of. And there are some people that have criticized, should we be spending $10 billion this way? And we can discuss that after the lecture if anyone wants to. But there's some things that we would like to know about the universe and our place in it that you can't figure out any other way but by having a telescope like this. And so one of those things that we would like to know is shown on this slide, where way over on this side, this kind of speckly stuff that's meant to represent something after the Big Bang, when the cosmic microwave background got emitted. We know that there was a Big Bang that started kind of our universe going, and then there was a period of time when there were no stars. There was nothing making light yet in the universe. And then after, and this is the big question, exactly how many hundreds of millions of years some stars and galaxies formed, and then you can begin to detect things. And Hubble got sort of out to about this point. maybe within 400 million years or so of the Big Bang. But there are so many reasonably sized galaxies that Hubble could see, we knew that there was other action that we hadn't detected yet. And if we really want to understand how did our own galaxy come to be and how is the universe working in this period, we needed a telescope that could see very faint things, because if you think of us observing over here, we're looking a large number of light years back in time. And those galaxies are very distant, and therefore they're very faint. And because of another effect that I'll describe in more detail later in the lecture, the universe is expanding because of some of the force imparted by the Big Bang. And if the universe is expanding, which we now are very confident it is, then everything's moving apart from each other, and almost everything we see is moving away from us, and therefore it's redshifted. And it gets to the point, meaning that if a star in one of these distant galaxies is emitting light like the sun, because it's moving away from us, it won't look like the color of the sun, it'll look much redder. And eventually you get to the point where you have to observe in the infrared, because everything has been shifted out of what we would normally think of as visible light. And so to find these most distant galaxies, there's basically no choice but to have a large infrared telescope in space, and it needs to be cold because infrared is basically heat radiation. And we don't want to just detect the telescope itself, you want to detect these faint distant galaxies. So that was one line of argument for building this kind of a telescope. Another is that we've discovered many planets orbiting around other stars. We call them exoplanets. And planets are best studied in the infrared because that's where they tend to emit their light, and that's where the molecules that we'd be most interested in another planet's atmosphere are best detected. In fact, this graph here shows wavelengths versus how much is emitted by the planet. And so this is an estimate of what an Earth-like planet, what its output would look like. And you can see these big dips, and that's where the molecules are absorbing the light that the planet would otherwise be emitting. And these wavelengths are exactly the range that Webb covers. And 0.5 here is what we would call visible light. So you can see that Webb goes way beyond the wavelength of visible light. And so another key project for Webb is trying to characterize these planets orbiting other stars, trying to understand their atmospheres. Can we find one that's like Earth? Well, we'll see. There are observations already planned that are going to tell us some of these things. All right, so why is it so important to be a cold telescope out in space? Well, this is a picture of a man standing in a blast furnace where I think they're melting iron to make steel. And he's holding a match. Kind of hard to see the match, isn't it? All right, well, if we take the blast furnace away, and the way we do this in space is that instead of allowing things to be warm, if you put a telescope in space, you can make it cold, and you don't have to worry about water depositing out on the mirror or part of the atmosphere freezing on it. There's nothing to get on the mirror in space if it's cold. So you can make the telescope cold, and bingo, you can see the match a whole lot better if you make your telescope cold. And some other things that are interesting about the infrared. Infrared wavelengths are very good at penetrating what you might think of as smoke if you're a fireman on the Earth's surface, but it also is good at penetrating the dust that's out in interstellar space. And it's also good for detecting the emission that a warm object like your body or the burner on your stove or whatever gives off. And so firemen often carry infrared cameras so they can see through the smoke and look for warm things that are where they're trying to fight the fire. And the same thing works for astronomers. So if you take a visible light picture, and this is an old Hubble picture here, where you can see these things that were called pillars of creation because stars are being born inside those brown-colored collections of gas and dust, that the dust is kind of obscures things and it hides what's behind. If you go to the shorter wavelength half of where Webb observes, the near infrared, those pillars start to become transparent. And then if you go to a longer wavelength, and now I need to find out if Webb's taken the picture of this region. This longer wavelength picture was taken with the Spitzer Space Telescope, and so it's not as tightly focused because that telescope was very small. But you can begin to see, for example, the top of this pillar here has a bright spot. That's a newly formed star. Pardon me. So by going from the visible into the infrared, you can get a very different view of what things look like. So large plus cold is exactly the correct description of the Webb Space Telescope. You'd think I was still in Arizona with being a dry throat here. All right, so just to give you some sense of scale, so here's the sun shield that lets the telescope get cold, and here's how Webb compares to Hubble, and you can already see how much bigger it is, and so it can see fainter things, and the size means that it can see as fine a detail at these longer wavelengths as Hubble saw at shorter ones. And it operates at a very cold temperature. That's what lets us see these faint things. And it has a variety of instruments, not just cameras, but also what we call spectrometers that split the light into colors, and we can use that to measure how fast something's moving away from us. We can use it to tell what the composition of something is. A lot of things come out of spectroscopy. And the original requirement was that the mission last at least 5 years, and that has to do with how long you spend testing it and so on. And in fact, the launch was so perfect that the amount of fuel that is left to help us stay in this particular orbital position would let us go maybe for 20 years. And so that was a real bonus that the Arians, yes, indeed. And the applause goes to the Ariane space launch team that made that possible. They did an absolutely perfect launch. So let's look a little bit at how come we had to fold up. So here you can see Webb kind of superposed on the rocket nose cone when it's fully spread out. And you can kind of see that you couldn't launch it that way. There'd be a lot of trouble if you tried to launch with stuff sticking out like that. So it gets folded up. And that's quite a trick to fold up a mirror, because usually you think of a mirror being made out of glass with some metal on it. Well, the trick here is that, like the Keck telescope that's on Mauna Kea, the Webb telescope is made out of segments, and you can see that if you go along a line for these in between these hexagons, you could define a place where you could fold it. And in fact, that's exactly what happened with Webb. So this center portion didn't have to completely unfold. These sort of outer wings were folded back. And of course, the sun shield also got folded up. And the sun shield is key to getting cold. Most of the cooling is just done by having black surfaces that radiate the heat out into space, and the electronics and things in the mission generate some heat. And it turns out that one of the four instruments, the mid-infrared instrument, has a little refrigerator to get its detectors even colder still, because working at the longest wavelength, it has to be the coldest. But most of the detectors can run at the temperature that can be achieved by just letting the heat radiate off into space. And so this shows you what the sun shield looks like when it's fully stretched out. There are 5 layers, and roughly speaking, the distance from one end to the other is about the size of a tennis court. So we're talking about a big thing to unfold. And it was the sun shield that a lot of people were worried about whether it would come out correctly, because it has a lot of cables and pulleys, and this material that it's made out of is a lot like the space blankets that you could buy at the hiking store for emergency use or whatever. It's very thin, metal-coated plastic and very floppy. And so engineers don't like it because something that unfolds out of solid pieces, it's always going to go to that place, but something that's a little floppy makes you nervous. So the job of the sun shield is to reflect back into space most of the sunlight that comes in and hits it. But with these layers, the other thing is that any heat that does seep through tends to bounce around and come out around these edges. And so it's very effective that this hot side, where the sunlight's hitting it, is warmer than room temperature. And then all the way over here, it's minus 388 degrees Fahrenheit. So that's a very effective heat shield. The one thing that was a little bit tricky about it is that, and gave a lot of trouble during the launch rehearsals and so on, if you deploy this sun shield on the ground, it's meant to be very lightweight because we don't have an infinitely large rocket to carry something heavy. And so it's very lightweight, and it would sag too much under its own gravity. And so it had to be what we call gravity offloaded. That made it very hard to pull it out on the ground. And it would take roughly over a month to properly stretch it out and another month to fold it back up. So it was hard to practice the deployment of this. So this shows kind of the schematic of how Webb moved around as it was getting built. So in the summer of 2017, most of the action at the project was at Goddard Space Flight Center, which is south of Baltimore and north of Washington, D.C. And we did tests of the instruments and so on there. And then it was put on a C-5A airplane, and the sun shield was not joined to things yet. This was just telescope and instruments. And it got flown to Johnson Space Center, and I'll show you a picture of the test chamber. And what we did there was actually test everything but the sun shield at the operational temperature that we would have in space. And we checked out the whole optical train, made certain that everything worked correctly. And those of you who follow hurricanes and remember the news, it was late summer 2017 when Houston, which is where Johnson Space Flight Center is, got hit by Hurricane Harvey. And we were testing, and we kept testing right through it. And it was a little bit unnerving to be in a building where the telescope was in a chamber that I'll show you in just a moment, and it was perfectly safe. But we were in this old building that had a leaky roof, and we had to stretch plastic out above our computers. But we kept going, and no one got hurt. Nothing bad happened in the end. But I really don't want to survive a hurricane when I'm doing something stressful like testing equipment. But that test worked out well. We actually finished on time in spite of the hurricane. And then everything got loaded up in the C-5A again. It came out here. It wasn't very far from here. It was in a big clean room up in Manhattan Beach. And it got mated to the sun shield and the spacecraft. Got tested some more, got shaken to make certain that nothing fell off due to the kind of vibrations the rocket would give it. And then it was put on a boat, went through the Panama Canal, and ended up in French Guiana, and then it got launched. So this is the test chamber that I mentioned at Johnson. It's a huge chamber. You can see from the size of the people how big it is. And it was originally built to test the lunar rover. So it was, and we had to do a lot of work to clean it up because it wasn't built to have delicate optics put in it. But this side picture shows you what it looked like with the telescope in it, and there was some test equipment up here. And this chamber got just as cold, got the telescope just as cold as it would be in space. This shows what it looked like going in and out of the C5A. It had this kind of thing that looks like an old Quonset hut, is actually a portable clean room, so that it was all sealed up, had a special airflow and temperature controlled and so on, so that the optics stayed good and clean. This shows what was going on here when the telescope part was mated to the sun shield. You can see it looks all kind of squishy when it's not deployed. And all of these things hanging down were cables that had to be mated, because underneath the sun shield is where what we call the spacecraft is, and the spacecraft is what sends the data back down to Earth or receives the commands up from Earth. And it's isolated from, this part, when we're in space, is all cold, and the stuff underneath the sun shield runs at more room temperature. And I don't think I would have wanted to be the guys having to lower this down and make certain all this stuff matched up, but they did a great job. Here it is, all assembled and ready to be shipped off to French Guiana, and you can see what it looks like in its folded up shape. You can also see how big it is by comparing to the people. So what's happened since we've launched? And that's where things are starting to get exciting, especially for me after waiting. Okay, so we made a lot of plans and rehearsed all of the activities that we were going to do, because we had to unfold the telescope. We then had to line up all those mirror segments so that they would act like a single smooth mirror, not 18 separate pieces. And then we also had to check out and start the calibration process for the cameras and spectrometers. And so the first part in orange was when the spacecraft got checked out and the sun shield was deployed. And then this green part is when we were aligning the telescope so that it would deliver the kind of image that we wanted. And then the purple part at the end is where the scientists really started getting excited, because we were lining everything up and really going at it. And at Space Telescope Science Institute in Baltimore, we had this room full of terminals. You can see these computer screens with all kinds of numbers that told us how things were working and so on. Okay, so what does this alignment process look like? Well, the estimates when we first got everything unfurled was that each of those 18 mirror segments might be pointing in a little bit different direction from the vibrations of launch and so on. And so therefore, when you looked at one star, you'd get 18 copies of that star, one for each segment, and that they would be spread out on some area of the sky. And the engineers estimated, worst case, they might be spread out over an area as big as the area of the full moon on the sky. And so we had this plan. You can see this kind of blue grid where my camera would take a series of pictures looking for the 18 segments. And we had it laid out to go over a big area of the sky. Well, we found them all in a very small area, which was the first clue that everything was going to really go well on this project. And in fact, that first collection of images doesn't look like much, but boy, I'll tell you, when we got this, I was ecstatic, because it meant that the light that hit the telescope was making it all the way down to NIRCam's detectors. There was nothing blocking the light. Everything was working, and of course, we still had to line them up because we don't want, if you want to detect something faint, you don't split it up into 18 pieces. You want them all piled up together. And so we had a very long, several-month process to take all of these and get them lined up. And I can give you a little clue about that in a second here. And along with these 18 images spread out across part of the sky, we also took what got dubbed the selfie. And I found this quite amusing because NIRCam has a feature in it where you can flick a lens into the beam inside NIRCam, and instead of focusing on far away things, you can focus NIRCam on the mirror. And the reason one of these segments is lit up is that was the one where, when we took the selfie, we were pointing, I think, maybe at this star most closely, and that's the segment that was lit up. And these things you see here are images of what hold up the secondary mirror. And it looks kind of fuzzy because NIRCam was not anywhere near completely cold, so things hadn't come into correct focus, but it did show that the alignment was what we had hoped it would be. So then we went and started looking at those 18 images. This picture now is where you took all 18 and put it onto one snapshot with NIRCam instead of having to scan all around. You can see that some of them look kind of funny. They're actually quite out of focus, but people who understand optics can look at these and say what you need to do to make them look good, to be good focus. And in fact, we actually had an automated routine to do that, although when people saw this picture, they were very happy because all of the shapes could be easily adjusted, taken care of by adjusting each mirror segment to make them look much better. And so what then happened is we went from these 18 scattered around to a beautifully focused star that had the characteristics as though the 18 mirror segments were just one smooth mirror, which was, of course, the goal of the alignment process. And so when this image came, again, there was another round of champagne toast, cheers, etc., because we'd proven that this idea of having a deployable telescope, that it could be aligned and that it could give excellent images. And so here's a more magnified version, and this starts to show one of the common themes that comes out with JWST images. So here's the star that we demonstrated the perfect alignment. But you notice some things in the background. There are a number of distant galaxies already showing up just in this image that was meant to show off the star. And I'll show some more of that. And one of the guys who is a member of the team expert at lining up the mirror segments, called the wavefront sensing team, went through that image and made a whole collection of all the different galaxies you could see in the background. And this was with an exposure that was it was barely over half an hour long. And it's just astounding that we're finding galaxies at this rate, many more than you find with Hubble. And of course, that was part of the point. By looking at longer wavelengths, we can see galaxies better. And so this is, for those that like numbers, what this is showing is that the kind of orangish line is sort of the theoretical best you could do, and the dots are what we actually achieved. And so this telescope, originally we thought at a wavelength of 2 microns, this panel here, that we would have a width of each star image. We thought that the width would be what we called diffraction limited. That is, you couldn't make it any smaller than that value, because that's what the laws of diffraction and physics tell you. But it turns out the telescope was working so well that we're actually diffraction limited at half that wavelength. Just amazing. I mean, we never would have promised that. So some of you may have heard that there was, the mirror has been hit by some micrometeoroids. And there was a budget for this. It was known that when you have a telescope without a shield out in space, little bits of stuff that like make meteor trails in our atmosphere at night could hit the telescope. And what was not expected, though, was that there would be one big enough that it would actually make a little dent. This, by the way, is not a crack. That's part of the picture of the strut that holds up the secondary mirror. And people said, gee, didn't that completely wreck the image quality? And one way to kind of quantify this is that before we launched, the requirement that the engineers were trying to achieve is what we call a wavefront error of no more than 150 nanometers. A nanometer is a billionth of a meter. So the kinds of surface irregularities we were talking about were pretty darn small. And in fact, we achieved 50 nanometers when we finished the alignment. We were 3 times better than what had been the requirement. And so when this micrometeorite made this little dent and caused some imperfections, the wavefront error only degraded to 60 nanometers, so only a little bit. And if the telescope quality had not been so good to begin with, we might not have ever noticed that this micrometeoroid had changed the image quality. And this particular dent, the people who study the distribution of meteors and stuff in the solar system were a little bit surprised that we got one with this much energy. And I'm just hoping that this was one-off bad luck. This hit, I believe, it was May that we got this hit, and there haven't been anything like this big since. So there have been some little tiny ones, but nothing like this. So once we got it lined up, it was time for the fun to begin. That is fun to the scientists. The alignment was fun for the engineers because the telescope actually worked as perfectly as the engineers ever said it could. And of course, that made them super duper happy that their designs and plans were correct. And the scientists were super duper happy that the engineers got it right. So we made a good team. So some of these are the early release observations that we took mostly in June, and then they were put on display they were released July 12th, and there's been a series of them continuing to come out, and every couple of weeks there's a new picture to look at or new result. And this one I'll talk about some more because this is one that is sort of a precursor to really going as hard and as deep as we can, taking as long an exposure as possible. But this is one of the first ones to really try to find very distant faint galaxies, and I'll show you how this compares to Hubble. This is an interesting collection of galaxies. These 3 are actually physically close to each other. This one just happens to lie along the line of sight. It's actually separated by quite a distance from the other 3. And if you go look at different versions of the early release observations, this particular picture is dominated by the mid-infrared instrument, MIRI's picture, where you can see this galaxy looks kind of funny, all filamentary, and it's showing the gas and dust in it. Over here is another one of the observations that came out not too long ago of a galaxy called the Cartwheel, where there was a kind of collision that changed it from being more, I think originally this galaxy probably looked something like this. But the collision changed the distribution of matter in that galaxy quite dramatically. And then this funny plot down here, This is another one of the key science areas. This is actually showing you that this exoplanet has water. So these wiggles are indicative of water. So we've proven that a planet orbiting another star has water in its atmosphere. And this is just, the first of many of these kinds of observations. As I mentioned, a clue that JWST is different is how often you see galaxies in the background. These two images are of a dying star that has thrown off the outer layers of its atmosphere. This is the short wavelength NIRCam image, and you can kind of see almost like shells of material that got blown off as the star was dying. This is the mid-infrared instrument that shows more where the dust and things are, and so again gives you a very different clue. But this, what I call photobombing images of the galaxies, it's just remarkable how often we see these. And I think if we thought back in retrospect, we would have said, oh yeah, Webb is so good at detecting galaxies, we should see them all the time. And I don't know how many of you noticed, I guess, geez, it's almost a month ago now, where there was a little bit of a scandal where a French scientist put a picture out on the web that was actually a piece of chorizo. And he said it was a Webb image of an exoplanet, which of course it wasn't, but it looked a little provocative. But there was another tweet that said, nah, that can't be a real Webb picture. There aren't any galaxies in the background. Okay, this is another picture of that grouping of galaxies that I showed you on the previous page. So as I say, these three are physically close together, and this one is much closer. And you may notice that if you look hard, this one looks a little grainy, and that's because it's just close enough that NIRCam can actually split up the light into the individual stars. And because the image quality is so good, even though this galaxy is much further away than we would have said we could do that before launch. Another thing I can mention about images, this is a star here that's actually a star in our own galaxy, in the Milky Way, that just happens to lie in this direction. And you notice that it has these spikes coming out of it. Those are what we call diffraction spikes, and you get 6 of them because of the way Webb is configured with the hexagons and the tripod that holds the secondary mirror. So you can tell if something's a star in the Milky Way as opposed to a distant galaxy by whether it has the little spikes coming out. And there have just been some amazing results when we compare the previous best images in the mid-infrared. This was taken with the Spitzer Space Telescope. This was probably taken around 2005. And Webb taking a picture of the same place, so you can see like these 3 stars here, and having a big telescope as opposed to Spitzer was a great mission for what it could do, but its mirror was smaller than 1 JWST segment. And so you can see the effect of making the telescope bigger gives you a sharper image, because this is exactly the same place on the sky, but we can now see much more of what's happening. So this is a repeat of that slide I showed earlier about that we want to try to understand these distant galaxies. And let me give you a quick understanding of how we can trace out some of the history of galaxies from these kinds of images. This one is blinking back and forth. That's the Hubble image. That's the Webb image. And if you focus on some places, you can see things that change quite a bit between the 2 images, for example, so that you can tell what's very far away, redshifted a lot, by comparing just these 2 images. But when I say that we're seeing a galaxy and we're saying, oh, that galaxy's age is only 400 million years after the Big Bang, how do we do that? How do I know what the age is? Well, it comes down to knowing how far away it is. So light moves pretty fast, but not infinitely fast. As Einstein is saying down here, 186,000 miles per second is not just a good idea, it's the law. Nothing can go faster than that. But that means that if, God forbid, someone turned off the sun, we wouldn't know it for 8 minutes. It takes the light from the sun 8 minutes to get to us. And the sun's pretty nearby. The light from the nearest star outside of the sun takes 4 years to get to us. And then what we're saying is that there are some galaxies that we can detect and study where it takes billions of years for the light to get to us. So the idea is that if we know the age of the universe, which we do from other observations, if we can measure the distance to the galaxy, and then we calculate how long the light has been traveling, then we can subtract that light travel time from the age of the universe, and that tells us the age of that galaxy. So how do we measure the distance to these things? We take advantage of the fact that Hubble, the man that the Hubble Space Telescope's named for, discovered this principle which you can actually derive from Einstein's theory of relativity, that as the universe is expanding and things are moving away from us, the distance of a galaxy is directly related to how fast it's moving away from us. Well, okay, but then you have to measure how fast it's moving away from us. Turns out that's actually quite an easy observation. So this shows the spectrum of a star that's not moving with respect to us. This is the kind of spectrum you might see if you were in the chemistry laboratory. And these lines are, if you have a source of light and you have some cooler gas, you get these lines. And this says that, oh, this line is from hydrogen, for instance. And chemists have nice tables of what all these lines, what elements they come from, what wavelengths they are. And so if we take another spectrum of a star that's moving away from us, you can see that these are shifted. And by knowing how much they're shifted, then we know how fast the galaxy is moving, and then we can calculate how far away it is and how long it's taken. Now we use this, astronomers like to call this how fast it's moving away from us, redshift. And redshift is proportional to how much the wavelengths get moved to the red. And so here's some redshifts, and this is how long it takes the light to come to us from something at that redshift. And this chart was made before JWST launched. In fact, it was made some time ago. So they stopped calculating at redshift 10, and now we need to go all the way up to 20, but that's a detail. And this is another way to look at it, so that this is how long it takes the light to reach us from something at these redshifts. And the math that relates these two is a little bit messy, so I kind of skipped that. I thought we didn't need a math lesson tonight. So this shows you how much progress we have made in finding these distant galaxies. And of course, with Webb, we don't know yet exactly what the limit's going to be that we can do, because we haven't taken the longest exposures yet, but we're getting a pretty good idea. And this shows some of the spectra schematically of galaxies that were taken in some of these early release observations. So you can see that this kind of structure, this spectrum, is moving to the red as the galaxy in question gets further away, and its age gets less and less the further away it gets. And now here's actually some real ones. So this is that same image that I showed you a little bit ago, and inside these little squares, here are the magnified views. This galaxy at the top, the light's taken 11.3 billion years to get to us. The one down here, it's taken 13.1. And you can see how these lines move to redder and redder wavelengths, and that's how we can calculate how far away it is and what the age is. So again, a repeat slide to remind us that another thing that we want to do is measure the spectra of exoplanets to find out what their atmospheres are like. And the way we do that with Webb is take advantage of what's called a transit, where the exoplanet goes in front of its parent star, and that makes a little dip in the light. And so here's another way to look at that. And there's a dip when it goes behind as well. And there will be some observations that take data all the way around, and if you do that carefully, you can actually see the difference between the daytime temperature on the exoplanet and the nighttime and so on. But what I want to talk about now is that if we take a spectrum of just the star and then take a spectrum with the star and the exoplanet, you can difference those and you can see what the effect of the exoplanet is. And this just gives you a sense of some of the kinds of molecules that Webb could detect. We might see ozone, we can see water, we've already seen water, we should be able to see methane, we should be able to see carbon dioxide, and just recently we did detect carbon dioxide. And there are more and other elements or molecules that we could see as well. So you can begin to get a sense of how we could tell, is this exoplanet like the Earth's atmosphere, or is it something poisonous that we wouldn't want to have anything to do with? And in fact, this is the one I showed before, so you can see these peaks are all labeled as water. And just recently, a lovely spectrum of carbon dioxide came out of another one of these kinds of measurements. So we're getting there. I should also mention that Webb can study things in our own solar system, and this is a very colorful picture of Jupiter. And again, it's false color. This is not what your eye would see. But you may notice that there's some interesting colors at the poles of Jupiter. And Jupiter actually has aurorae, just like we do on Earth. It has northern lights and so on. And so one can actually learn things about a planet like Jupiter that you would think we would know everything from flybys, but Webb actually has a bigger and different range of wavelengths it can study. And of course, Webb can look at it repeatedly and look for weather changes and so on. So to sum it up, this telescope is working fabulously. There's lots of places on the web, on the WEB web, where you can find pictures. This is one of the most recent ones to be released, which again is a star-forming region in a galaxy nearby. You can see there's a bright star cluster here that you don't see so well with MIRI, but you can see the effect of all the interstellar gas and so on. So stay tuned, lots more good stuff to come. And thanks for being a good audience.